All right, I just started recording. So, like I was saying, ketose is a sugar with a ketone group. The closed ring form of a sugar can look like either a hexagon or a pentagon. A furanose is a six-membered sugar ring that looks like a hexagon, and a furanose is a five-membered sugar ring that looks like a pentagon. So I remember this by thinking about how furanose starts with 5, so furanose 5, whatever helps. Okay. So I believe we did a topic session that goes more into detail about stereochemistry, but I included this slide so that we could go over the basic concepts for a short while. So two molecules are enantiomers if they are mirror images of each other and they cannot be superimposed, meaning that if you place the molecules on top of each other, they won't give the same molecule. So enantiomers may have stereocenters or chiral carbons. A chiral carbon is a carbon that is attached to 4 different things and lacks an internal plane of symmetry. If you look to the right, you can see examples of chiral carbons. You can determine whether the chiral carbon is R or S, and then based on these designations, you can see if the molecules are enantiomers. We'll practice this in a short bit. So one thing that the MCAT might ask from you is to find the number of stereoisomers a molecule has. Of course, you don't need to draw out all of the possible stereoisomers. Instead, you can use the formula 2 to the power of n, where n is the number of chiral carbons. So let's practice our R and S conformations using the molecule on the right. So actually, I have a better example for us to do later. So does anyone have any questions about enantiomers or the equation I gave? Okay. So I have a question for you guys. I'll give you about 2 minutes. Type your answer in the chat when you're done. Okay, Brian, why do you say C?
Because according to the formula 2 over the power of the number of isostereomer, in this molecule, it has 3 stereocenter, and the stereocenter is defined as 4 different groups, stereo specifically.
Yeah, exactly. Yeah, so the molecule has 3 chiral carbons and 2 to the power of 3 is 8. So the molecule has 8 stereoisomers. That's pretty much as far into detail that you have to know about this. So moving on, a high yield topic for this unit is absolute configuration or L/D configuration. Why do we need to know absolute configuration is a great question, but a lot of biochemists use it in order to differentiate sugars by focusing on the chiral carbon that is furthest away from the carbonyl group. If the alcohol group on this carbon here, the one in red, is on the left, then the molecule is an L molecule, which is easy to remember because L for left. And if the alcohol group is on the right side, then the molecule is a D molecule. Does that make sense?
How do you know which alcohol you're looking for?
So it's always the alcohol group attached to the carbon that's furthest away from the carbonyl here. Okay. All right, so you might also be asked about specific rotation, which is designated as plus or minus rotation. An important thing about specific rotation is that you cannot tell whether a molecule is plus or minus unless you run an experiment or it tells you in the passage. The sign of plus or minus just indicates what direction an enantiomer rotates a plane of polarized light. So if it's clockwise, it'll rotate in a positive direction, which is a plus. If it's counterclockwise, it'll rotate it in a negative direction, which is a minus sign. Again, not really high yield, but I have seen a few questions that's like indicate the specific rotation of the molecule below. And the options will be minus, plus, plus and minus, and cannot be determined without more information. So of course, that last option would be the right answer. Okay. So let's talk about Fisher projection. Fisher projection is just a vertical way of drawing a molecule. So the figure on the right, the far right, shows you what direction the substituents on the carbons are pointing. So substituents on the sides are always out of the page. So hydrogen and the alcohol group. And substituents on the top and bottom are going into the page. So this CHO group, the ketone, and the CH2OH group. So when you're looking at a Fisher projection, the horizontal lines are always wedges and the vertical lines are always dashes. So for the molecule on the left, is this a D or L configuration? All right, so the molecule is a D molecule because the alcohol group that's attached to the chiral carbon farthest away from the carbonyl is on the right side. So its position on the right side makes it a D molecule. If it was on the left here, then it would be L. All right. Okay. So no, D and L is not the same as S and R. Very important to think of them as two separate things, at least for MCAT purposes. If a question is telling you, or if a question is asking you to identify whether it's D or L, you don't think about S or R, you just focus on the alcohol group that's farthest away from the ketone here. Or not the ketone, the carbonyl group. If a question is asking about S or R, you just focus on the chiral carbon that you're being asked about. So knowing that the horizontal lines indicate wedges, let's practice assigning R and S configurations. So is the chiral carbon on the top here R or S? No, there's not really a correlation between those conformations. You have to think of them, you have to think of them as separate things. Okay, so the conformation is R. So remember that after assigning priorities, you have to flip the conformation that you get if the lowest priority is facing out of the page. So instead of an S conformation, it will be R, because like we said, these horizontal lines are pointing out of the page. And hydrogen is the lowest priority group, so we have to make it into the page. A useful tip that I learned is that for sugars with the most oxidized carbon at the top here, a chiral center with the hydroxyl group on the right will be R, and the chiral center with the hydroxyl group on the left will be S. So since this hydroxyl group is on the right, it'll be R, and this one would be S, and then R since the hydroxyl group is on the right, and then R again since the hydroxyl group is on the right. Does that make sense? Okay, so yeah, R for right. So you assign numbers based on the substituent that the carbon is attached to. Like for example, yeah, based on priority. So looking at this carbon over here, the hydroxyl group is the first priority because the carbon is attached to an oxygen. And the second priority here would be the carbonyl group, since it's a carbon attached to, or like double bonded to an oxygen. And then the third priority would be this carbon, since it has like a higher molecular weight than this hydrogen over here. The hydrogen will always be lowest priority. Okay. And for the mirror image of D-glucose, the R or S configuration will be reversed. So we can see that each an enantiomer assignment is, or sorry, each stereocenter assignment is reversed. So that's how we know that these two are enantiomers. All right, so let's move on to diastereomers. So two molecules are diastereomers if they are not identical, meaning that they are not superimposable and that they are not mirror images, unlike enantiomers, which are mirror images. So this diagram looks chaotic, but it actually helped solidify my understanding of diastereomers and enantiomers. So the lines in blue indicate diastereomers and the lines in red indicate enantiomers. The diagram is saying that molecules A and B are enantiomers, which makes sense because they are mirror images and both stereocenters are flipped. So these two R's here become two S's. The same thing goes with C and D. This S and R are flipped to R and S here. All right, now let's look at the diastereomers. So A and C are diastereomers because they are not mirror images of each other, and only one R is flipped to an S. The same thing goes with B and D. Only one S is flipped to an R. Does that make sense? Okay. So let's talk about epimers. An epimer is a type of diastereomer. So two molecules are epimers if they differ in configuration at one chiral center. So for this second carbon here, carbon number 2, is it an R or an S configuration? Okay, so it's an R configuration because if we remember the rule that I mentioned a while back, if the hydroxyl group is on the right, then the chiral carbon would be an R, like R for right. So, all right, and looking at the molecule on the right here, is this carbon R or S? Yeah, so it's S. And these carbons here, carbon 3 and carbon 4 for these two molecules have the same configurations because the hydroxyl groups are in the same place. So this one is S and this one is R. This one is also S and this one is also R. So they differ in conformations at one carbon, which is here, because this one is R and then this one is S. So therefore, these two molecules are epimers. Oh, I had my animation there. All right. So I have a question for you guys. All right, GOT, why do you say A?
So if it's an enantiomer, it has to be exactly the opposite. And so you're looking for something that would be the exact opposite at each point, which is A.
Yeah, exactly. So yeah, you were right. The correct answer is A. We're trying to find the configuration of the stereocenters for an enantiomer of beta D glucose. So like I said before, enantiomers are mirror images of each other. So all of the stereocenter designations are flipped. So to answer this question, all we have to do is flip the R's and the S's. Okay. So moving on. Carbohydrates exist in equilibrium as either a linear or a ring structure. In order to get the ring structure, the alcohol on the carbon farthest from the carbonyl attaches or like attacks the carbonyl here. You don't need to know what causes the cyclic structure to come about, just the general idea that the alcohol on the carbon farthest away from the carbonyl attacks the carbonyl. All right. So, as we know, the boat conformation is the most stable conformation of a cyclic structure. In order to draw the boat conformation, you have to number the carbons starting from the carbon with the double bonded oxygen, so the carbonyl. Then you go down until you reach the CH2OH. So once we have the boat conformation, you number your respective carbons. So I usually remember the first carbon as being the one on the right of the oxygen. The numbering continues clockwise and ends here at the 6th carbon. So to determine whether the OH groups point up or down, you have to look at their position on the Fisher projection. So OH groups on the right will point down. For example, the OH group on the 2nd carbon points down in the boat conformation. OH groups on the left will point up in the boat conformation. For example, the OH group on the 3rd carbon is pointing up here, and therefore in the boat conformation, it'll point up. So notice that the ketone group is converted into an alcohol group. This alcohol group can either be up or down. It doesn't really depend on anything since it can rotate freely. The CH2OH group on carbon 5 will point up if the molecule is in the D conformation and will point down if the molecule is in the L conformation. Since this molecule here is a D glucose, the CH2OH group will point up in the pyranose. Yes, I mean chair conformation. I have no idea why I said boat. I'm so sorry. I meant the chair conformation. Does anyone have any questions?
Yeah, I just wanted to confirm. So with the structure on the left, the glucose, I guess you're suggesting that depending on the side the hydroxide is, that'll indicate whether it's up or down in the boat conformation or the chair conformation?
Yeah, exactly. So if it's pointing on the right, it'll point down. If it's on the left, it'll point up.
Okay, thank you.
Okay. So let's talk about anomers. So two molecules are anomers if the hydroxyl group on the anomeric carbon are in different positions. The anomeric carbon is the carbon from the ketone group, so carbon number 1. These two glucoses in the figure are anomers. So the hydroxyl group on the molecule on the right points down, making the molecule alpha. The hydroxyl group on the molecule on the left points up, making it beta. So I remember this by drawing the letter A. When you draw the tail, you draw it downwards. Let me try to do it. You know how like when you draw the tail downwards, that's how I remember like down means alpha. So since this hydroxyl group can indicate, so this hydroxyl group can exist in either the alpha or beta conformation. Therefore, it's said to be in mutarotation, which essentially means equilibrium between the alpha and beta conformations. Oh, that's so cute. Buttercup is face up. I love that. It's so much better than mine. I thought I was so clever with the drawing the A. All right, I have a question for you guys. All right, so the correct answer is C. To find out if the molecule is a D or L sugar, we look at the anomeric carbon. The CH3 group on the highest number chiral carbon, the one circled, is pointing down. Therefore, the molecule is in the L conformation. Since the hydroxyl group on the anomeric carbon is pointing up, we can say that it is in the alpha anomer conformation. A big thing is having these rules memorized. I remember I had a note card with these rules taped on my wall, and I look at it every single day to have it memorized. So constantly revising these rules helps a lot. Yeah, so the anomeric carbon, I always think of it as like the one on the, that's like directly attached to the oxygen group on the right, because when you're thinking of it in the Fisher projection, the alcohol group on the ketone that's farthest, sorry, the hydroxyl group on the carbon that's farthest away from the carbonyl attacks the carbonyl. So if you, I guess, like, let me draw it. Oh, here, let me see if I have a drawing here. So this is what I'm talking about. Like the hydroxyl group attaches this carbonyl here, and then you can see that carbon 1 would be the anomeric carbon because it's attached to the oxygen here that attacked it. So the anomeric carbon is carbon number 1 always. Okay. All right, I have another question for you guys. All right, so for this question, the correct answer is A. We're looking for a 5-carbon chain with an aldehyde. We can immediately cross out C, B, and D because they are all ketones. Option A is the only one with an aldehyde, and the hydroxyl group on the anomeric carbon is on the left as well. So we know it's an L-aldopentose. Does that make sense? Okay. All right, so let's get into monosaccharides. Some common monosaccharides that you should memorize are glucose, which is the sugar found in the blood, fructose, which is sugar found in fruits and is also sweeter than glucose. You should remember that fructose is a furanose or a 5-membered ring. You don't have to know like the directions the hydroxyl groups are pointing. And galactose, which makes up the disaccharide lactose and is less sweet than glucose. And the last question, yeah, well, yeah, let's look at that. Yeah, so all of these are ketoses. Okay. So before I get into glycoside formation and disaccharides, I want to first quickly introduce the functional groups hemiacetals and acetals. A hemiacetal is a carbon attached to two R groups, an alcohol group and an ether. An acetal, on the other hand, is a carbon attached to an R group, two ethers, and a hydrogen. Reducing sugars are basically sugars with at least one hemiacetal. On the top right is an example. Looking at the sugar on the right, you can see the hemiacetal, which is here. So why do we call it a reducing sugar? Because it can be oxidized by compounds such as copper and silver. We'll get into this in a bit. Non-reducing sugars, on the other hand, do not contain hemiacetals and are locked in this closed ring structure, meaning that they are not in equilibrium with an open ring form. So since they're locked in this acetal form, they can't act as reducing agents and therefore are unable to be oxidized. Does that make sense?
I have a quick question.
Yeah.
So for the hemiacetal for the top picture, it's not exactly matched to the hemiacetal on the lower left picture. Is it we only look at the OH and the OR? That's colored?
What do you mean the one that's colored?
Like the one on the bottom saying
Yeah.
hemiacetal. This is showing to R group. But the one showing actually in the disaccharide is actually one of them is actually H. Does
Yeah.
it need to be exactly matched
No.
with the hemiacetal?
No. It doesn't exactly have to be two R's. It can be an R or an R. I'm so sorry. It could be two R's or an R and an H.
I see.
So hard
Thank
to
you.
say. Yeah. Okay. So why do we care about hemiacetals? The first reason is for glycoside formation. Glycosides are bonds between the anomeric carbon and an oxygen attached to an R group. So looking at glucose here, for example, and you don't need to know the exact mechanism, but the hydroxyl group is kicked off, creating a carbocation. The electrons on the oxygen then attach themselves onto the carbocation, forming this ether here. And this bond between the anomeric carbon and the new oxygen is called the glycosidic bond. Another way to look at this reaction is seeing that a hemiacetal is converted into an acetal in the presence of a hydroxyl group. Does that make sense? Okay. So we have two tests to determine whether a sugar is reducing or not, which are called the Benedict's and the Tollens test. In the Benedict's test, an aldehyde or the open ring form of a sugar is oxidized and a red precipitate is formed. In the Tollens test, the same thing happens, except a silver precipitate is formed. Again, you don't need to know the exact mechanisms, except that if a sugar is reducing, then it'll be red in the Benedict's test and silver in the Tollens test. Okay. So disaccharides are formed when the electrons of an alcohol group attack a carbon on another sugar. So looking at this example, the alcohol on the fourth carbon of the sugar on the right, this one over here, attacks the anomeric carbon on the left sugar, causing the alcohol to leave and a glycosidic bond to form. To label this, we need to indicate whether the bonds are alpha or beta and what carbons are involved. In this case, the first carbon and the fourth carbon are bound to each other. And since this alcohol, the alcohol is pointing down, since this oxygen is pointing down, it'll be an alpha 1 for glycosidic bond. There isn't really a way to predict whether a glycosidic bond will be alpha or beta. The only thing that will really be asked of you is to identify whether a glycosidic bond is alpha or beta and what carbons are involved. Does that make sense? Okay. So I have some practice questions for you guys. What type of glycosidic bond is the first one? Is it alpha, beta, and what carbons are involved? All right, so the first one is a little bit tricky. It's actually an alpha 1,2 glycosidic bond. So alpha because the oxygen is pointing down, 1 because the first carbon here is involved. But when we look at the sugar on the right, what do we notice? All right, so we notice that it's kind of symmetrical. You have the CH2OH groups here on both sides of the oxygen. And the OH groups here, if the oxygen were a monomer, and this OH group here. So we'll label this carbon as 2 because it would be the same as if it went the other way. So labeling this carbon as 2 or this carbon as 2 doesn't really make a difference. Does that make sense? Okay. Yeah. So the unique thing about this sugar here on the, well, it doesn't really matter if you go clockwise or counterclockwise because in the end it would be the same thing since this molecule is symmetrical because you have the CH2OH groups here and then the same thing over here. And if this, pretend that this sugar is a monomer, you would have an alcohol group here and an alcohol group here, which are like on the same sides, and then this alcohol group here. So if you label this carbon as 2, it would be the same thing as labeling this carbon as 2 because they're symmetrical. Does that make sense? Okay. All right. And what about the second disaccharide here? Yeah, the second one is beta because the oxygen is pointing up, and 1 because the first carbon here is involved, and 4 because the fourth carbon here is involved. So what about the third one? Beta because the oxygen is like pointing up.
So I guess what I'm wondering is you're looking at that oxygen pointing up, but then what about the other carbon? Isn't that pointing down?
When in an ideal world, I would love for this oxygen or like for these bonds to look like a little triangle, but I got this picture from a textbook and they drew it like that. So I guess that's like the scientific way of drawing beta bonds. But yeah, an easy way to distinguish between alpha and beta is that alpha, it looks like they're holding hands. Beta, it's like this weird N thing. Mhm. All right, and what about the third one? What type of bond is that? Yeah, it's alpha 1,4 alpha because the oxygen is pointing down, they're holding hands. 1 because the first carbon here is involved, 4 because the fourth carbon here is involved. All right, I have a question for you guys. Okay, so for this question, the answer is B over here. So in choices A, C, and D, we have hemiacetals. So this free hydroxyl group is hanging here, ready to be oxidized. It's next to the oxygen here. All of these guys are hemiacetals. But if we look at choice B, we don't have a hemiacetal. The oxygen, instead of being here, is all the way over here. So the only thing we have is an acetal. Does that make sense?
So
Yeah.
you don't look the connection between two saccharide. You only look the one on the most right.
Yeah, because the connection here that you're talking about, it's always going to be an acetal since this carbon is attached to like the hydrogen, the R group, and then these two oxygens here. These two ethers, I guess. So you would always look at the one that's like all the way at the end and see if
I
it's a hemiacetal or an acetal.
Thank you.
Okay. All right, let's talk about polysaccharides, which are basically just repeating monosaccharides. The most important ones you'll need to know are starch and glycogen. Starch molecules are just glucose molecules on repeat, and they are connected by alpha 1,4 glycosidic bonds. That you do need to know. And glycogen is basically the same thing as starch, except that they also have alpha 1,6 glycosidic bonds to allow for branching, which is what makes glycogen such a great molecule for energy storage. Okay. I have a quick question for you guys. Okay, Brian, why do you say C?
I think basically, if you look at the Fisher projection, if this is on the right side, you will assume all of them point down. If this is on the left side, you point all of them up, and then you basically just look into each of the carbon on the ring.
Okay, so the correct answer is D. So starting with carbon 1, which is this anomeric carbon on the ring, the alcohol. So the alcohol group exists in mutarotation, which can be either up or down. So we're not really too focused on the first carbon. Moving to the second carbon, the substituent points down because the alcohol group is on the right in the Fisher projection. So you were right on that part. The alcohol group on the third carbon points up because the alcohol group is on the left. The OH group on the fourth carbon points down because the OH group is on the right. Finally, the CH2OH group points up because the molecule is in the D conformation, because this alcohol group on the carbon farthest away from the carbonyl is on the right side.
So just a quick question. So we always, for that first OH group, like we always skip that one? Is that what you're saying? Like it can, it's a flexible OH? It can
Yeah,
either
pretty
be-
much.
Okay.
Because it's an equilibrium. Does that make sense? Okay. All right, so this is the last concept we'll talk about, which is amino acid synthesis. So there are two reactions you should be familiar with. The first being the Strecker synthesis. The first step involves an aldehyde, ammonium chloride, and potassium cyanide. You don't need to know the exact mechanism, but I drew it out for your reference. If you combine these reagents together, you get an aminonitrile, which is this structure here that has the NH2 group and a nitrile group over here. So that's step 1 of Strecker synthesis. Step 2 of Strecker synthesis is the creation of an amino acid. Through a series of steps that you don't need to know, the nitrile is converted into a carboxylic acid when water and acid are present. The result is an amino acid with an R group that came from the original aldehyde. So again, you don't need to know the mechanisms, just the starting material and the reagents. Does that make sense?
So overall, what would you say is the goal of a Strucker synthesis?
So the goal is to create this amino acid backbone using only an aldehyde, NH4Cl, and potassium cyanide.
Okay, thank you.
Okay. So Gabriel synthesis is another way to synthesize amino acids. It's a little less complicated. The starting material is potassium phthalimide, which is this big structure here, along with a base and the base over here and a halide. The R group of the amino acid comes from the halide. That's the biggest thing that you need to know about Gabriel synthesis. Okay. So does anyone have any questions? Because I have a passage for us to do together. I can give you 10 minutes to finish it. It has 5 questions, or I think it has 4 questions actually. And they're not super complicated, so they're not gonna like completely destroy your brain. It's up to you. Do you guys want to do the passage?
Yeah.
Okay. All right, let me just stop sharing my screen and I'll send you the link.
Just quick question. So we don't need to know the specific mechanism or how the compound is attack where for the Gabriel synthesis and Stryker synthesis. We just
No,
need to know
no.
the starting material and they produce amino acid.
Yes.
Okay.
Mechanisms are like very low yield.
I see. Thank you.
No problem. I just sent the link in the chat. So I'll give you about 10 minutes to finish it. When you're done reading it and answering the questions, just type done in the chat. Not a lot of questions show up with Gabriel synthesis. I was actually looking for some and I couldn't really find any, but yeah. All right, it looks like the majority of you guys are done. All right. So any volunteers for the first question? You can just type your answer in the chat as well. All right, Brian, why do you say D?
Because only D have this hemiacetal, which is shown in the most right.
Yeah, exactly. Yeah, so reducing sugars have the hemiacetal, and Brian is right. Subunit 4 has the oxygen here in the hydroxyl group, so it's a hemiacetal. And for the next question, what did you guys get? Okay. All right, so we can eliminate A and C immediately because we just identified subunit 4 to be a reducing sugar and therefore a hemiacetal. Subunit 2 is an acetal because this carbon is attached to the 2 oxygens here. So our answer is B. Okay. And what about the third question? What did you guys get? Right, so the correct answer is D. We have 5 units of unsaturation because we have 4 rings and 1 double bond here. Adding this together, we have 5 degrees of unsaturation. And for question 4, what did you get? Brian, why do you say A?
Because the bridge carbon on the left is point down, and if you count the number of the carbon, the first one on the left, on the right will be 1, and then the connecting one on the next one will be 4.
Yeah, exactly. Right, that was a perfect explanation. And for question 5, what did you get? Okay. So subunits 1, 2, and 3 are all locked, especially subunits 2 and 3 since they are acetals. Subunit 4 is a hemiacetal and will display mutarotation, meaning that this alcohol group can either exist up or down. So it'll alternate between alpha and beta. Does that make sense?
The malrotation is basically mean the free conversion between closed ring and the linear chain.
So mutarotation refers to the equilibrium between 2 different stereo chemistries. So subunit 4 existing as alpha or beta would be considered mutarotation because this hydroxyl group is like free to rotate. So it's said to, sorry, what?
That does not count the one on the most left. They only count the one on the most right.
Yeah, because subunit 1, like this, subunits 1 and 2 are kind of locked into each other. But subunit 4 is like free to rotate here. The hydroxyl group is free to rotate. Does that make sense?
Yes, thank you.
Okay. All right. Does anyone have any other questions?
I just wanted to clarify.
Yeah.
So for the reducing sugars,
Okay.
what it like just in like a quick summary, how do you know if it's reducing again?
If it has a hemiacetal,
On the further right side, right?
yes.
Okay. All right. Got it. Thank you.
The definition of like the reducing sugar is that it has to contain at least one hemiacetal, but it can technically, like, it's 99% of the time it's on the far right side. But the trick is to just look for a hemiacetal, which is basically just a structure.
Okay. Thank you.
Does that explain your question, GOT? The, like, how do you recognize a hemiacetal?
Yeah,
It's
so
just- yeah.
it would be the one with the hydroxyl.
Yeah, so the hemiacetal, I think so the hemiacetal is usually in this conformation here. It has this structure. It's basically a carbon attached to an R group, another R group, which could technically be a hydrogen, like this one over here, an ether, so this oxygen here, or and the hydroxyl group. The main difference between the acetal on the top and the hemiacetal on the bottom is that only the hemiacetal has this hydroxyl group. So you can kind of like identify that, identify as this carbon as being a hemiacetal because this oxygen here would technically, sorry, the hydroxyl group would be like this one in blue, this oxygen would be that one in red, the R group would be like this carbon here, and this other R group would be the other like invisible hydrogen. Okay. So any other questions before I go to sleep, even though it's 9:30? All right, so thank you guys for coming to today's topic session. I hope you found it useful. I'll be sending out the slides and the recording in like a few minutes. No problem. I hope it helped. Yeah, we will be doing more sessions in the summer. That's also another thing that we've kind of been struggling with, is that we've like done these topic sessions for a while now, and we're kind of so we've covered a great deal of topics, so we don't really have any ideas as to like what to cover next. So we really want your guys's input. So in the survey that I'll be sending later, please like indicate like what you want to see from us. Do you want to see us repeating more sessions, or do you like want to watch the recordings later, etc.? Repeat. Okay. I was advocating for repeating the topics, but yeah. All right. Okay, so keep an eye out for that survey. Okay. All right, have a good night, everyone. Yeah, I understand that entirely. All right, good night. Thank you for coming.